actually. It's not going to be that bad at all. First of all, is z a function of two variables? Yes, it is, right? Z is y squared minus x squared. So I have a very, very nice formula for this, right? The formula is the double integral over d of the square root of 1 plus the partial of f with respect to x squared plus the partial of f with respect to y squared dA, okay, with respect to area. So notice that I'm not using partial of f with respect to u and partial of f with respect to v because I'm going to leave x and y as x and y. So instead of switching over to u and v, I just leave it as x and y. So the formula changes a little bit. Now to do this, let's go ahead and take these partials. What is the partial of f with respect to x? Negative 2x. Partial of f with respect to y? 2y. Okay, let's go and let's fill this in a little more. Double integral over d of square root of 1 plus 4x squared plus 4y squared dA. You following me? That's just 1 plus each of those squared. And then now what? What do you think at this point? Drum roll. This is your good old surface sitting up there, right? We want to find this integral right here over the domain D with respect to area. Where's the domain? What are your variables? X and Y. Where is that? Where are X and Y? Down on the ground, right? Do you have any restrictions on X and Y down there? Do you see the shadow of this thing on the ground? It's a ring, right? It's a polar. It's polar, right? So imagine projecting this down onto the xy plane. Right now, this is what we're talking about when we're talking about D. We're talking about this thing. That's D. That's our domain. Because our domain is on, the restrictions are on x and y. So this is perfect for polar. Perfect. So I'm going to switch to polar now. So to go to polar means I need to have some grasp on how to define D in terms of polar coordinates. So switching to polar, can you give me some restrictions for theta and r? 0 to pi? 1 to 3. So that's going to give us the stuff between the two cylinders. And now I'm ready to switch this integral over. So this double integral is now going to go, doesn't matter what order, because they're both limits are constants. And then square root of, another drum roll, 1 plus 4r squared. Good. So where's that coming from? Yeah, this right here, if you just take out the 4, you're left with x squared plus y squared. But when you go to polar, this is r squared, right? So that becomes r squared. And then we need something else, r. So that r is outside the integral. And then d, this we do need to make sure we get it right. R and d theta. There we go. U sub, basic U sub. There's u, the derivative, we're off a little bit. And yeah, I think that's very doable, right? It's very doable. Let's go ahead and just crank it out real quick, just so we'll have the answer. Hi. Whoa. Zero to 2 pi, 1 to 3, square root of 1 plus 4r squared times r. dr dt. E.
That's gross.
Yeah. But we can go change that. We'll get a numerical answer. Sorry, an approximate answer. There's the exact answer, 1/6 of all that stuff. But an approximate answer, about 111.988, is the surface area of that thing. Pretty cool though, right? It's pretty cool that you can find the surface area of something that seems so complicated. All right. So if you have a function of two variables, I'm so tempted right now to try and come up with a formula for the surface area of a cone. I don't think I've ever done that before. But see, if I were really going to do that, I would really prefer to just use Cal 2 to do that. Right? Like, let's say someone gave you a cone, and you wanted to come up with a formula for the surface area. And they gave you, this is height, and they gave you that this is the radius. Then the surface area of that, the entire thing, would be pi r squared plus, so pi r squared is the bottom piece, right? But then you need the area of the cone part. Agreed? Agreed. So you could do this with what we just did, because you could just find the equation of that surface, that cone. That would be your f of x, y, and then you go through and do all the partials. But the easier way to do this would be this.
It's a solid revolution.
That's right, solid of revolution. So take that right there, that line segment, and rotate it around the x-axis and find the surface area of revolution. That's easier, I think, than this, but it could probably be done. So we're not going to do it. All right, moving right along. Yeah, that's it. There's a bonus problem that I'm going to offer you there. Right there. It's number 56 out of the book to be turned in at the final. And I believe I have an animation that helps you understand it. Let's see if I have that. Thought I had it.
Sir, is our curriculum going to go all the way through the day right before the final exam?
Yeah, I've never finished early in this class, but we might have a little bit of time. Yeah, read that, and if you have any questions on it, you can come ask me and talk to me about it. You're trying to find the surface area of the intersection part of two pipes. But it's in the book, so it has an image for you, all right? All right, that's it for 13.6. So 13.6 was just about, can we draw a surface, first of all? Okay, now that we can draw a surface, can we find tangent planes to surfaces? Yes. Can we find the surface area of the surface? Yes. Okay, so now we go to 13.7. And now we talk about surface integrals. So this is where I kind of started with. Let's say we have a surface. Let's say we know the density at every point, then we can come up with the mass by just adding up the densities, the masses at every single point on the surface. So this is going to start with a definition. So this is the first time that we're seeing something here. Double integral over the surface of the function of three variables. So you have some surface here, S, in three-dimensional space, and then you have a function over here that's taking each point on this surface, plugging in and giving a numerical value. So it's almost like I said, if you knew the mass at every point, right, we'd like to add them up to get the total mass. Or if you knew the temperature at every point, then this would be like the sum of all temperatures, which doesn't make a whole lot of sense. But The idea is that you have a numerical quantity attached to every point on that surface. So this is the domain. This is the domain over here. And then what we're going to do is we're going to see what does that mean? Well, this means, what does D capital S mean? We know what D little s means, right? D little s meant with respect to arc length, right? D capital S now for us is this. And what is this? It was after tangent plane. This is something. This is surface area. So what we're doing is we are integrating this function of three variables over the surface S with respect to surface area. With respect to surface area. The way I like to imagine this is what we're doing is we're taking this little infinitesimal little patch on here, right? We're taking a little infinitesimal patch, that's this piece, and we're multiplying it times that, which is like the height of the function there, even though this is in 4 dimensions, so you can't really, it's just like a quantity there. So it's like we're taking some point right here, and let's say we know the mass at that point, and then what we're doing is we're multiplying it, or no, sorry, the density at that point, and then we're multiplying it times the area, and that will give us our mass. Does that make sense? Okay. But again, this doesn't have to be density function. It can be any function. So this is called a surface integral. So look at the formula for it. This becomes, we know this ds is this. We just did that in the previous problem. But this right here, remember what that notation means. It means you're going to take the scalar function and evaluate it at the vector function. So that means you're going to plug in, you're going to replace with x the first component of this vector function, replace the y with the second component of this vector function, replace z with the third component of this vector function. So we're going to do an example, but that's the notation. So let's do one. Find the double integral over S of xyz ds, where S is the part of the unit sphere above the cone, z equals the square root of x squared plus y squared. Do I have a picture? If I do, I'm not going to show it to you yet. Yep, I do have a picture. Let's try and get our heads around what S is. So for S, we have the top half of the unit sphere. Okay, we know the equation, that's x squared plus y squared plus z squared equals 1, right? And then the cone, z equals square root of x plus y squared, x squared plus y squared. And it's just the top part of that cone, so that our cone comes out like this, like that. And they hit here, don't they, somewhere like that? See that? So we're talking about this surface right in here. It's like just the top part of like a little snow cone, just that top surface, right? Now this is this should look familiar to you, for those of you who did the mini exam that had a problem like this. We need to come up with a way that we can represent this surface S with some vector function u, r of uv. Unless you can do it, unless you can be sure that this is just a function of just two variables, like x and y. So you have with these problems you have two options. You either get everything in terms of u and v and do your cross products, or you try and do that shortcut. So what do you all think? Do you think that you could define that?
Yeah.
Yeah? Go for it.
Never mind.
Okay.
You need numerical values.
Well, I need to know how I'm going to define that thing. Like, You know on the take-home part last week, I said take these home bonus questions and what we were doing last class? That's what we need to do for this. We need to figure out, can we define this surface as a function of two variables? So do you agree it's part of a sphere?
Yeah.
Okay, so we could use the sphere equation, the sphere vector equation we just used in the previous examples, right? But we have some restrictions here. We're not going to draw the whole sphere. We're just going to draw this top part. So can you give me any restrictions on this? We know we're going to go all the way around, right? Like this? Can you give me any restrictions on this part? How far we drop down to draw this thing?
That would be pi over 4.
Yeah, that would be 5, but we're using, what were we using? I'm going to go back to the one that we had. I want to stick to the same thing so we don't have to redo all our math. Okay, this one right here. So R of uv was sine u cosine v sine v, I'm sorry, sine u, sine v, and then cosine u. So the u is like our phi, right? The u is like the phi. So what is the restriction on u going to be to draw this? Don't you need to know, like, the angle, right?
0 to pi over 4.
So we're trying to find this angle right here, right? That's our u. So how do you know it's pi over 4?
Just the angle that the cone's at, or the cone makes an angle of pi over 2 total, so it's split in half.
So you're sure that cone is 45 degrees? You're sure it's not? I just want to be convinced, that's all.
Because there's no scalars on x or y, that cone equation gives you
What might help is if you just tell me where that point is. Where do they hit each other? So think of it this way. If we take this picture and cut it in half, let's just cut this picture in half and open it up. What are you looking at?
Pi over 4 is the only
Circle.
one where you take the x and the y and square and you get 1.
Oh, I
And
can
get-
see a way to do it.
And get 1?
Yeah. Right?
But what 1 are you talking about?
Well, because the z is supposed to be 1.
I'm just trying to be convinced that this cone doesn't look like this as opposed to that, or like this.
So we have the z equals x squared plus y squared.
Yes?
And so the point at where they equal each other, you set.
Okay, there. Yeah, that's what I wanted to hear. You're saying if you take that and put it here?
Yes.
Yes. Okay. Did you have another suggestion?
Yeah, I was going to say, but I was going to put it the other way around. I was going to say put z squared is equal to x squared plus y squared from the cone.
Yeah, you could do either way. Now, if I plug this in for here, right, we're going to have two variables in one equation, aren't we? Right? So my suggestion here is if you cut this in half, right? And take a look at it, peel it open, take a look at it. Isn't this the picture you would see? Yes? Okay. So if I do this, then if I cut it in half, I've made either x0 or y0. Do you agree? Like if this is my x-axis coming out, right? If I cut this in half, let's say that's x, and open it up, maybe x is 0 then here, right? So if x is 0 in this picture, then what do these two equations become? Y squared plus z squared equals 1, and that equation becomes z equals absolute value of y, but we're up, yeah, so let's just say y, right? Z is y. So now I have these two equations. Now I'll just take z and throw it in there, right? And I'm just going to have y squared plus y squared equals 1, and that means 2y squared equals 1. That means y squared equals 1/2, and that means y is equal to the square root of 1 over 2, which is the same as root 2 over 2. Right?
less than or equal to, was it, 5
Phi, 0.
is equal, and then less than or equal to 2 pi, and then divide that by 2, and then you can get,
Wait, say that again?
never mind. No.
Sure?
Yeah.
Okay, I'm going to go back to this picture. This is the y-axis. This is the z-axis, right? I've cut this thing in half, which means really x is 0. What I've determined is that if I do this, the y-coordinate must be root 2 over 2. So this right here, that point right there, the y-coordinate right here is root 2 over 2, which means this side is root 2 over 2, right? And this right here, from here to here, is what? 1, because you're on the sphere, the radius of the sphere. And then you could solve for this side and get root 2 over 2. These two sides have the same length, which means this is pi over 4. It's 45 degrees. All right? So I guess what I'm getting at is if this was changed to 2, let's say in front of that, then you're no longer at 45 degrees. That changes it. So you have to somehow figure out what that angle is. So can I move on now? To draw this top cap, what I'm going to do is use this thing which draws the whole sphere, but I'm going to put some restrictions on my u and my v. My v I want where, and my u I want where. So I still want to swing all the way around, 0 to 2 pi. So that will spin me around like this, but I want my phi, or in this case my u, to only go down to pi over 4. So 0 to pi over 4. Okay. Is that all right? Now let's set up this double integral. Okay, double integral over S of x, y, z d capital S should be equal to, okay, double integral. I'm going to leave it. I'm not going to do anything here yet. Let's just talk about what x, y, and z are. So what's x, y, and z?
X is sine u cosine v.
Yep, so this is going to be my r function. This is the surface. That's my x, y, and z. So I need to take this, sine u, cosine u, right, times y, which is this one. Yeah, I don't know why I did that. V, sine u, sine v, and then cosine u. Okay, so that's just x, y, z from the vector function. And then I need ds. Now remember what ds was. ds was the magnitude of the cross products, magnitude of the cross products of the partial derivatives, dA, right? That's what that is. So do we know what the magnitude of the cross product of these the partials of this is? We did all that, didn't we, already? We did that? It was just sine u, okay? So this part right here times sine of u. Okay, so this piece right here goes with all that. And then that other piece goes with this, but I still need some stuff out here. What do I need? That dA part, right? And that dA is going to come from these two things, right? So I'm going to have, with respect to u and v there, and the order won't matter because these are constants. So I'm going to go ahead and go, what do you want to do first? U? V? V first, then u. And that means on the outer one, I'm going to go 0 to pi over 4, and on the inner one, I'm going to go 0 to pi. There we go. Everyone understand where that all came from? So if we hadn't done that problem before, right, we would have had quite a bit of work in store for us, right? We would have had to have taken the partials of this, crossed them, taken the magnitude, done all that work just to get this one little piece right here. And now let's try and put all that together. Let's see if we can't simplify this. I hope it simplifies to something. Let's see. Sine of u, how many of those we got? 3. Sine cubed u. How about cosine u's? Just one of them? And then how about sine of v's? Just one. How about cosine of v's? Just one? Right? Do we all agree with that? Now, this is something I'm going to bring up from way in the beginning when we were first doing double integrals, that I know on the mini exams, I did talk to some of you about this. At this point, yes, you could integrate this with respect to v, and then after you're done with that, plug everything in and go with respect to u. But since this is separate from this, like the v's and u's aren't mixed together, right? You can just do this. You can go and set up 2 integrals. The first one will go 0 to pi over 4. And this will just have the what stuff in it? The u stuff, right? I'm separating my u's from my v's. Then say times, not plus, 0 to 2 pi, and then sine v, cosine v. If you don't like this, if you don't want to do that, you don't have to. But I'm using the fact that this right here is some function of u, and this right here is some other function of v. And so if you have them completely separate like this with multiplication, you can separate this into 2 integrals. All right, can we do this one? I think this one can almost be done mentally, I hope. Antiderivative of that, 1/4 sine to the 4th u, evaluated 0 to pi over 4. Right, because just basic u substitution. Let this be your u substitution. Derivative of sine of u is cosine u du, right? So you have basically, this will turn, I can't use u because I'm already using u. So it'd be like w substitution. So this is w, this is dw, and then w to the 3rd power is 1/4 w to the 4th. So y'all, after looking, see, agree? Okay, that one's that. And then times, this one is the same exact thing. I'm going to use that for my w substitution, and there's the derivative of it. So that just becomes 1/2 sine squared v, and then evaluated 0 to 2 pi. The answer is 0. That's kind of a sucky thing that just happened there. It's 0 because this part, right? 2 pi, sine of 2 pi is 0, and then sine of 0 is 0. So we wind up getting 0 right here, and then times that. So just remember, we are not finding the surface area of this anymore, right? What we're doing is we're saying, hey, look, we've got this cap, right? This little dome piece, this little surface up here. And what we're doing is we're saying, hey, take every point on this right here, every point, and take those points and plug them into this function right there and add them up. Okay? So it's like, let's say you plug that point in there, you plug it in, and you get, let's say, the number 3. And then you move to another point, and you plug it in, you get the number 2. And then you plug all the points in. When you add them up, some of them turned out to be positive, some of them were negative maybe. And when you added them all up, it all came out to be 0. Make sense? Okay. That's kind of, I don't like that gave us 0, but would have been more interesting if we had a nice answer. Oh, there's that piece that we were talking about. Where's my, oh, there they are. Okay, there's my sphere and cone. We were trying to find a way of representing that. Now, I am curious, though, whether or not you could have done this a different way. Let's see how many more notes I have with this. Yeah, we got 10 minutes. Yeah, let's not do it the other way. Because of time, let's just move on. All right, so given a scalar function f on a surface S with the equation z is equal to g of xy, then we can use parametric equations, blah, blah, blah. So all this is saying is, in the previous section, I just said that, hey, if we want to find surface area, we've got to do the magnitude of the cross products, and that can be troublesome. If z is a function of x and y, then we can use this shortcut formula, right? This is saying if you're trying to do this integral right here, and your surface is a function of x and y, then we can still use the shortcut. But we're using g here instead of f because f is the function right here, so we can't use f twice. So f is the original function of 3 variables. When we're defining the surface, if it is a true function of x and y, then we can use the shortcut piece right here. So an example of this one would be, let's say if we want to do this, let's say we want to do this surface integral, okay? I'm going to have to scroll up, so I'm just going to put it here. What if we want to do that where here's our surface? It's all of this, the whole thing. Okay? So I would like us to evaluate that surface integral over this entire surface, which means we're going to have to break it up. Our entire surface is the whole thing. So how many surfaces do you see here? 3, right? You've got this part, you got the green part that wraps around, you've got this part on the back side, right? So what we're going to do is we're going to call it like S1, S2, S3, and then we're going to say that this integral is equal to the double integral over S1 plus the double integral of S2 plus double integral over S3. Got it? Okay. What's S1? Where do you want to start? S1? Okay, x is 0. That's the backside? X is 0? Okay, can you give me a vector function that would draw that for you? Now, you have to be real careful here, everyone. You want to draw this backside. Okay, and the x value here, the x-axis is this axis right here. So how can you draw me that? Okay, so 0, right? X is 0. We know that part. But you got to draw me just that disk, though, right? You can't draw me just the whole plane. Just want that circle. So, do you know the radius of it? You know it because of this, right? Because of that. That cylinder going this way is giving you the radius of that red circle in the back. And this has a radius of 1. Do you all see that? So you were right. Okay? It should be, what do you want to do? Cosine u, sine u. I'm missing something. What am I missing? A v. So you tell me. Where's the v go? I want to draw the whole disk, right? The whole disk, not just the outer ring. I want the whole disk. V cosine u. Come on, Robert. V cosine u, V sine u. Right? That's R1. What are our restrictions on V here? And U? 0 to 1 for U. And for V, yeah, V was 0 to 1, wasn't it? U was 2 pi. Okay, that'll do it. All right. Let's get S2 before we do anything else. Let's get S2. What's S2? Let's do, you want to do the cylinder or do you want to do the plane? You want to do the plane? Let's do that one. X equals 1 minus Z. So how are you going to draw that for me?
I can see where you're doing it.
What's that?
Use your same y and z from R1, but instead of being 0, x is going to be equal to that component is z, and x will be 1 minus d sine u.
Okay, so basically you're going to do the same thing here because you want to draw that disk, but you want to like stretch it out the x-axis. So the x is going to be what? This plane equation, right, tells us what x needs to be. X needs to be 1 minus z. And there's z. So this should be 1 minus v sine u.
And we can just reuse our restrictions.
And just reuse your restrictions. See, this is why I wanted to go over those things last class. Do you see that? Because the book doesn't go through any of this, and it would be like throwing you right into the fire right now, right? Without you having any sort of idea of what I'm talking about with these, it might be a little hard to grasp this. How about the cylinder part, S3? S3, which is the part that is this. All right. So what can you tell me about this vector function, R3 of uv?
The y and z are the v cosine and v sine.
Okay, do you want v though? Do you need the v? Because if you're drawing this green part, is your radius going to change? Like if I start drawing this, right? Like you draw it like this. I want to maintain the same radius the whole time, don't I? That green cylinder?
But isn't it filled in?
It's not filled, well, it's filled in this way, but no matter how, like if I turn my point of view of this thing, of this green cylinder, right? That's me looking down the green cylinder. The green cylinder is actually just out here, right? Like that radius never changes on the green cylinder.
So it's not like in the back where we had to calculate the whole.
That's right. The whole thing is,
But then won't our calculation make it shallow on the inside? Or like empty? It won't.
it will be empty, yes.
So how do we know to calculate it as a solid versus as an empty shape?
Well, it's not a solid. None of these were solids. Like this was a back disk, right? This was a disk that's been stretched out, but it's still a surface.
So we're just, okay, just checking.
So we don't need the v part. We can still do cosine u and sine u, and that should give us circles. But our x-coordinate needs to be somehow controlled. Yes?
Could you go over again why here you don't include the v, but then on the top one you do? If the v is already set between 0 and the radius isn't.
Okay, when I draw this,
Yes.
okay, let's fix a v, all right? So if I look at this 3,
Oh, okay, I see what you mean now, but then how come for this one you don't need the v?
because your cylinder's not a disk.
Yeah, because look at how it's pictured right there. When you do like the blue part, you're starting from the center
Look.
and you're drawing outwards.
Yeah, the green piece is what we're trying to draw right now,
You're only drawing the edge.
right? The green piece is what you're drawing. So you're only drawing this outer part, right?
Oh.
You see? You're only drawing that.
From the origin.
And so you don't need it to go any, like you don't need the radius to go in. You need the radius to fix. The thing you need to control is this x-coordinate has to always be
Stop on a plane.
stopping at this plane. That's the part we need to control with the v part. So how are we going to control that? Kind of. I'm running out of time. So here's what it is. Go home and think about it. V, okay?
We use restrictions on v.
And then we use restrictions on v within when we define v. So u is going to be between 0 and 2 pi. Okay? That's gonna draw us circles, right? Then-
Is from 0 to that.
Then our v is between 0 and 1 minus z, but for us that's 1 minus sine of u. Okay, so I have 30 seconds. The idea is this. Give me a u, all right? So let's go with an angle here. Let's go with 0. So if I do cosine of 0, what's that? 1 sine of 0, 0. So that means my y-coordinate's 1, and my z-coordinate is 0. So I don't go up or down. So I'm right there, right? That's where I am so far. Came out on the y-axis 1. Now, I'm there, but now what I'd like is for you to let your x-coordinate be v. And v is stuck between 0 and 1 minus sine of u. What was u again? 0. So sine of 0 is 0. So I want to be stuck between 0 and 1. So now what I'm going to do is draw from 0 out to 1. And I'm going to draw that piece. And then if you change your angle, make it like pi over 4, then see, you're going to be like, I think, hold on, 4u, root 2 over 2, so something like this, and then like that. And then if you come down here, it'll go like this. I'm out of time. We'll have to pick up on this one, all right? We've got our surfaces, and now we have to go compute those surface integrals for each surface. So we've got to do derivatives, cross products, derivative, cross product, magnitude, derivative, cross product, magnitude. Lots of calculations. All right. Have a good day. Isn't there a take home?